Dimensional analysis. So dimensional analysis is a technique for doing conversions and calculations. But before we get into that, let's just sort of spend some time looking at these kinds of calculations. I want you to think about it. If you have to pause, that's fine. And look at them and really think about, what do you need to do with the units? That's often what's different from math class. In math class, you're rarely dealing with units. In science class, we have all these units. So hopefully what you came up with was that in the first case, I have centimeters on the top and centimeters on the bottom, and those are going to cancel out almost as if they're variables, like x's. So an x on the top of the fraction and an x on the bottom would cancel out. However, grams and milliliters cannot cancel out, so I would be left with final units of grams on the top divided by milliliters, so grams per milliliter. On the bottom, when I go to add grams and milliliters, I can't. I can only add things that are the same. If I'm trying to count how many apples I have, I can't add in oranges because oranges weren't the unit. This is apples, so you can't add apples and oranges and get an answer that's either apples or oranges. So you cannot do any mathematical pluses or minus unless the units are the same, which means sometimes that I have to convert one of them so that I can add them together. Okay, with that, let's just kind of bring up a couple other things that are different about math and chemistry. We both use math, but sometimes the way the chemists use math is a slightly different application. The math is the same, but the treatment is a little different. So a lot of times in algebra, we have a variable assigned to just a value, just a number. But remember, our measurements are now going to have a unit associated with them. So a unit is a variable in itself. So a unit is, for instance, a particular length, or how many the times an atom can vibrate, or there's different kinds of creations of what these units are. That's the SI units. But they each stand for something. And then when I can relate two different units of the same property, or even of two different properties sometimes for a specific substance. So I can relate grams and milliliters for water or for ethanol. And I also have lots of math equations, right? All those equations they give you are relating two different variables. So we're really relating two different variables. This is the trick of dimensional analysis. In dimensional analysis, what we're doing is we are multiplying a number that we already have by the number 1. So it's not changing the actual value of the number, but it is changing the units, because I'm going to multiply by a fraction that has a value of 1, because the quantity on the top is equal to the quantity on the bottom. And I get those informations from my relationship of my two units. So in that case, I can cancel out the units, complete the multiplication, and I have successfully converted from feet to meters in this case. Okay, so I want you to practice, because of course I can't make conversion factors until I can write down equalities. If I want to make a conversion factor between meters and centimeters, I have to know an equality between meters and centimeters so that I can create a fraction. So just take some time and try to create these. Some students really struggle with it, making it in this form, but a lot of times you can say a sentence. So if you ask me to write an equality between ounces and cups, I'm lost. But if you say, tell me a sentence relating ounces and cups, you can say, oh, there's 8 ounces in a cup. Well, that really is the equality. So, if you can say, well, I know a yard has 3 feet. There's 3 feet in a yard. So say it out loud, write it down, and then convert it to a math equation. Okay, so there's basically 2 types of mathematics we're going to do in chemistry. And one is this dimensional analysis, and another is by equation. So these are 2 ways that I can convert different properties. So the dimensional analysis is only if the 2 substances are directly proportional. Remember, directly proportional means that I have something equal to something. There's no plus or minus. There's no squaring. It's a direct equality with just a number in between. So if they are directly proportional, then I can use dimensional analysis. I'm going to start with a known measurement, write all the known relationships as conversion factors, and set up a calculation so that the units cancel out. But The problem is I have to write these conversion factors, and that's the part where usually there's a barrier. But this is typically how we're going to convert pounds to grams, gallons to quarts, mass to volume, grams to moles. They don't have to even be the same property, right? Mass is a different property than volume, but as long as I have some conversion information for a specific substance, I can use this technique. The other method is by an equation. So I have a custom equation that relates two different things, two different properties. And then I'm going to use algebra. I'm going to plug in the information I know and use algebra to solve for the thing I'm trying to find. But I need to have a formula. So in chemistry, for all the different kinds of relationships we had, that would be a lot of formulas. So we're going to rely heavily on this dimensional analysis method. But there are some things where you just have to use an equation. We've seen a few of them already, right? Mass number and numbers of protons to neutrons. That's an addition, and I have to know that relationship to do that. Fahrenheit to Celsius is going to be another one. Okay, so when we're ready to do dimensional analysis, I first start by write the starting unit with its units off to the left. Usually we begin at the top of the page on the left side, and I'm going to write what I'm trying to get to, the units alone, in the upper right. So I kind of have a destination in mind. Then I'm going to fill in conversion factors with just units. So I'm going to make a fraction that just has units on the bottom and units on the top, but no numbers. And I'm going to develop a strategy that's going to get me canceling out units from my starting units to my desired units. So if I'm starting with grams and I need to get to kilograms, I would have grams on the bottom of the conversion factor and kilograms on the top. And you may need more than one. You may need to sort of stack it and say, I can't get there directly with one, but I know a relationship between grams and kilograms, and I know another relationship between kilograms and cubic meters, and I have another between cubic meters and gallons. And so you may have to sort of strategize and use multiple conversion factors. So you're just doing the units. Then I'm going to go look up for equality information. Now I'm going to fill in the numbers by making sure that I am going to make sure that the top of the conversion factor and the bottom of the conversion factor have the same value. They're equivalent to each other. And that way, overall, the fraction has a value of 1. And then I'm going to multiply everything on the top, divide by everything on the bottom, get an answer, and I can finally check sig figs. But the part that people go wrong on is trying to figure out, when you have a problem, what information in the problem is the starting measurement, the thing I'm trying to convert, and what information is given to me to make conversion factors. And that can be a little tricky. Okay, so I'm going to go through making 3 types of conversion factors. Let me fill this out since it's not in the right order. Okay, again, if I know an equality, so I know that 1 inch equals 2.54 centimeters, that can be used to make a conversion factor. So note that because 1 inch is equal to 2.54 centimeters, I can put the 1 inch on the top, or I can put it on the bottom. In both cases, remember, our conversion factor has to have equal values on the top as on the bottom, and both of these conversion factors fulfill those requirements. But what we're going to find out is that this one was useful for canceling out centimeters as my starting units, and this one is useful for canceling out inches as my starting units. So when it's useful is going to change. So, and I'm going to be able to make everything into 2 conversion factors. So sometimes making one of them is easier than the other, and then I just flip it to make another one. So another type of information you can be given in a problem is something per something. Gallons, miles per gallon, grams per milliliter. So per is a mathematics word that means divide, and essentially that's giving you the conversion factor. It's just giving it to you in words. So if you were given 39.6 grams per mole, whether it's written like this in the problem or whether it spells out grams per mole, that means 39.6 grams goes on one side of the fraction. The per is the dividing line, and everything after the per goes on the bottom. So 39.6 grams per mole. If it doesn't have a number, it's assumed to be a 1 mole. Now, what's very important, though, is that once I have this one, I can flip it to get the alternate one. Sometimes this is the one I'm going to need. So I want to make sure I write this one, and it's not easy to see that here, but it's pretty easy to see that here. It's pretty easy to flip it. The final one that's usually the trickiest is percent values. Again, percent is a mathematical term. Percent means per 100. So I can divide the number given before the percent by 100. And it's always a ratio of a part to the whole thing. So percent values are, and in many cases they're less than 100 because the part is smaller than the whole. So if I see 15% sodium chloride solution by mass, so this is now where the units are really tricky to figure out. I know it's 15 over 100 because that's the 15%. But now how do I decide what is the part and what is the whole thing, and how do I decide what units are appropriate? Well, that's where I really have to say, so when they're saying sodium chloride solution, even though we're not talking about solutions yet, we know this is describing a mixture, and sodium chloride is one thing in the mixture along with water. So this is going to be sodium chloride on the top and the whole thing, the solution on the bottom. And when it says by mass, that means I need to pick a mass unit. You can pick any mass unit, but you better pick the same. Once I have the first one, I can flip it to get the second one. This is going to take practice. Writing conversion factors is a tricky thing. Okay, so let's look at some examples. A golfer putted a golf ball 6.8 feet across the green. How many inches does this represent? This one's not too hard because there's only one number here. So 6.8 foot has to be my starting measurement. And I set up a conversion factor. I would first set it up just with the units of inches on the top and feet on the bottom. Then I go looking for that information, or maybe I'd be searching my brain and say, do I know a sentence that relates feet and inches? Yeah, I know there's 12 inches in a foot, at which point you put the 12 with the inches and the 1 with the foot. And now I do the math. 6.8 times 12 divided by 1 equals 82. An iron sample has a mass of 4.5 pounds. What is the mass of the sample in grams? And it gives you some equality information following it. A kilogram is equal to 2.2046 pounds, and a kilogram is equal to 1,000 grams. Well, this information clearly must be for the conversion factors. It's relating to different properties. So I'm going to assume this is for the conversions, and then 4.5 is my starting number. Now, since I'm starting with pounds, I know my first unit must have pounds on the bottom. I look to see, well, the only thing that has pounds is relating it to kilograms, so I put kilograms on the top. Then I put kilograms on the bottom of the next one, and I say, oh, I have kilograms to grams. Finally, after I've set up all the units, then I go back and fill in the numbers. 1 goes with the kilograms, 2.2046 goes with the pounds. 1 goes with the kilograms on the bottom, and 1,000 goes with the grams on the top. Finally, I will complete 4.50 times 1 times 1,000, divide by 2.2046, divide by 1. And of course, you can skip the multiply and divide by 1s because they're not going to change the value. So this is how I'm going to complete dimensional analysis. The hard part is not the math. The hard part is the setup. So I want you to practice. How many inches are in 16.3 centimeters? Here's another one. This is a little trickier. Convert 155 square feet to square centimeters. Note that the information I'm giving you is that 12 inches is equal to 1 foot and 1 inch is equal to 2.54 centimeters. But you have to think about, well, what do you do with the fact that this is talking about squared and squared? Are the relationships true when I square these units, or do the relationships change? We will go over these in class. We'll also go over some harder ones. I want to show them to you before we get to class. These are much more tricky. A recipe calls for 3.0 pounds of lemons. If an average lemon has a mass of 65 grams, how many lemons are needed? I want you thinking about which information is really the measurement that's being converted and which information is given to me to help me build conversion factors. And this is another one that's similar and much more complicated. How many kumquats are there in 14.2 glips of xenol? There are 35.7 glips per gander of xenol. There are 1.35 times 10 to the 14 kumquats in every gander. Again, which number is my actual starting measurement? Which numbers in here are given to me to be conversion information? And I intentionally created this problem with things that make no sense, because sometimes we can use dimensional analysis as a strategy when I'm a little bit unclear on what these things are. You don't have to know what kumquats and clips and xenol are and ganders are. You can just say, I'm going to take this information, I'm going to use my math skills and get an answer. It'd be better if these were things that we're talking about that had some chemical relevance, that you understood the concepts, but sometimes just getting there by calculation can get us there.